Good afternoon to everyone. I welcome all of you to the 53rd lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. I am happy to introduce today's speaker, Dr. Arnab Ghosh. Dr. Arnab Ghosh completed PhD in the year 2005, 15 at Indian Association for the Cultivation of Sciences, which is one of the premier institutes in India. He then moved to Israel to carry out his postdoctoral studies. After carrying out postdoctoral studies at Mdan Institute of Sciences, Israel, about 4 years, he came back to India and joined as an assistant professor in the Department of Chemistry, IIT Kanpur. Dr. Ghosh is working on statistical mechanics of fermionic systems, open quantum systems, and quantum thermodynamics. In my view, all these areas are new emerging ones. Dr. Ghosh has published a considerable number of papers in these areas. Currently, he is supervising a couple of students. I came to know about Dr. Arnab Ghosh a year ago when I came across one of his works, Microscopic Quantum Generalization of Classic Leonard Oscillators, which he put in the preprint server archive. I found that paper was very interesting and I asked one of my students to work it out. When I requested to deliver a lecture in this forum, Dr. Arnab Ghosh immediately accepted our invitation and allotted a time for us. Thank you, sir. With this short introduction, now I invite Dr. Arnab Ghosh to deliver his lecture. Over to you, Dr. Arnab Ghosh.
Yeah, thank you so much for the kind introduction. I'm really feel honored to get this chance because it's clear that I'm not really an expert on nonlinear dynamics. As you heard that in my PhD I worked on dissipative quantum systems, and then right now currently my interest mainly on quantum thermodynamics. And I'm happy to share one of the news that one of our recent work has featured in physics recently, where we have, formulated a systems of quantum thermal transistors. And this is the reference. So whoever are interested in, you can look up. But in this conference, this is a online lecture series on nonlinear dynamics. So I am not going to talk about this thermal transistor today. So what I decided, particularly for this online series, that recently, as Professor Santival mentioned, and that we have done some work on microscopic quantum formulations of classical Leonard oscillators. Since I had this background of open quantum systems or dissipative dynamics, particularly I'm interested in that, and you all know that particularly in this audience I don't need any introductions, that this Leonard oscillators is essentially a nonlinear dissipative systems. And so the natural question is that, is it possible to formulate a microscopic picture for that? So with this interest, we worked on this problem. So this is what I am going to present today now. And since I have joined IIT Kanpur very recently, so this fundings is definitely given by initiation grant of IIT Kanpur and also the startup research grant from ACRB. Okay, so with this, so this is the kind of outline. So what I will do, as I mentioned, so I will first give an introduction of what is the fundamental difference between the classical dissipations in classical systems and the quantum systems, how to introduce that, and how to formulate dissipation in quantum system, systematically or consistent way. So, and then I will discuss the theoretical formalisms and its results. Finally, I will conclude. Now, as I mentioned that I am not a real expert in nonlinear dynamics, so I was introduced to nonlinear dynamics during my MSc by Professor Devshankar Ray, with whom I did my PhD. Okay, he did a lot of work on nonlinear dynamics, and the work that I am going to present, all these analytical work and particularly the numerical implementations was done by my project students, I mean past projects, MSc project students, Srijan. So he was a very good student. He is currently now in Colorado Boulder for his PhD. And this is the reference, what I'm going to present today. So I'm not going to, refer to the other, references in the individual slides. So this is, everything is there, all these relevant references. Okay, so with this, so let us start. Now, as you all know that classical dissipations, the most simplest one is the damped harmonic oscillators. And this is the equation of free harmonic oscillators, x double dot plus omega 0 square x. This is the free harmonic oscillators. Now, in most of the situation of the classical systems, the dissipation are introduced in a most phenomenological way into the equations. Now, if you introduce that, then the equation becomes this. And you know the solutions. The solutions is a damped harmonic oscillators, which shows these characteristics. Now, once you make this introduce quantum dissipations, the same problem, things becomes much more intricate because of the fundamental uncertainty principles. If you take the same systems like the harmonic oscillators, if you write down the quantum Hamiltonian of it, so H is equal to H bar omega 0 a dagger A, then, and write down the Heisenberg equation of motions, then without any dissipations, this is the first two terms will remain, right? So dA dt is equal to minus I omega 0 A. So that's the free harmonic oscillator term that is there. But now with the same philosophy, if you introduce dissipations phenomenologically in this equation, Heisenberg equation of motion, then it will be this differential equations and you can solve it. And the solution is given by this one. Now, this causes a serious violations of the laws of quantum mechanics. As evident, if you calculate the commutator between the A and A dagger at long time, because of the presence of this e to the power minus gamma by 2t, this commutator vanishes. And this is a serious violations. This cannot be. Because in quantum mechanics, it says that the commutation relations between the operators must always be preserved at all times. And to circumvent this problem, one of the, this most popular strategy is to construct what is known as the system-reservoir theory. What does, in this system-reservoir theory, people, is the following, that one consider a small system of your interest, the dynamics of which you are interested in, you consider that as your system of interest, and you consider that the system is coupled to an infinite degrees of freedom, which acts as a bath, okay, which remains at some temperature, and the system is coupled to these reservoirs. Then what happened? The system loses its energy to the bath in the form of dissipations. On the other hand, bath provides energy to the system in the form of noise or fluctuations, such that there is a balance between this noise and the dissipations. And this balance is in the form of the fluctuation-dissipation theorem, such that the total systems becomes thermodynamically closed. So this system-reservoir model, therefore, plays a very, powerful methods and very popular systems, treatment for understanding a wide variety of topics ranging from macroscopic quantum coherence, heat conductions, relaxation processes, directed transport, Brownian motions, stochastic processes, and so on. And also in my PhD, I worked on some of the topics, like particularly these relaxation processes in quantum optics and reaction rate theory and so on. But in most of the situations in this system-reservoir model, this coupling between the system and the reservoir is taken to be linear. And this gives rise to the linear damping. Okay. So, on the other hand, linear damping. On the other hand, you can understand to address this Leonard systems, which is by default a nonlinear dissipative systems, we make this coupling to be nonlinear, and that's, you know, makes life complicated. I mean, this is makes the problem very non-trivial. And in fact, in my PhD, I attempted the same, and we failed, completely failed. The reason I will make it clear as we go along. It turns out that but this time we have succeeded. The reason is that time what we have tried to do is that we right now started deriving this, you know, the system reservoir theory based on these coordinates and the momenta. On the other hand, this time we find out that the second quantized, if you write down the system reservoir Hamiltonian in terms of second quantized picture, things becomes much more tractable and one can solve it. Okay, so this is what took a long time, but anyway, so the question is, you have to make this coupling between the system and the reservoir nonlinear. On the other hand, normally this coupling is taken to be linear, which gives the linear damping. And one can understand that in order to be consistent with the system reservoir theory, since there must be a fluctuation dissipation relation such that the total system and the reservoir is thermodynamically closed, this dissipation is always accompanied by a noise. And these noise always present there from the microscopic picture, even at t equal to 0. Because this is the origin of quantum noise, which remains even at t equal to 0, and you can think of this is due to the vacuum fluctuations. So the origin such that even at t equal to 0, you can have a fluctuation dissipation relations. So you can understand that the microscopic basis, once you introduce dissipations in quantum systems, things becomes much more, you know, different and intricate. So with this in mind, we are interested to now look at these Leonard systems. And what you know, that classically, although quantum mechanical systems must have this noise and dissipations, always it has to be there, but classically, you know that these Leonard systems without these noise terms exhibits, because of the presence of this nonlinearity in the dissipative term of a classical systems, may lead to interesting physics and complete modifications of the dynamics, and in fact it may result in the formations of what is known as the limit cycles. And I don't need any introductions to this audience. What is the limit cycle? This is an isolated closed trajectory in the phase plane, and I have taken this picture from the classic books of Strogerge. And the Leonard systems represents a prototypical examples of such classical nonlinear dissipative systems, in particular van der Pol and Rayleigh oscillators. And what I am going to do, discuss in this talk, is to formulate a microscopic picture of this van der Pol and the Rayleigh oscillators. Now, why is it so? Because if you look up that these van der Pol and the Rayleigh, these are two examples of the Leonard oscillators. It has this first two terms is precisely the harmonic oscillators, and this third term corresponds to the nonlinear damping term. So, in the microscopic theory, I can model this first two term as starting with a harmonic oscillators. I can model that as an harmonic oscillators, and the nonlinear coupling, I will try to get this form of the nonlinear coupling by suitable choice or judicious choice of my nonlinear interactions. Okay. So, is it audible? Just to check, cross check.
Yes, sir. We are listening.
Okay.
Yeah.
Okay, perfect. Okay. So then that's the whole idea. Okay. So this objective, now you can understand that the idea is to search for a quantum analog of classical Leonard oscillators within the framework of the system reservoir theory, so that I can get this kind of equations. Okay, now these equations I should mention at this point the formalism that I'm going to present, in some sense, it is very different from the method that was developed by in our institute physics department, Sagar Chakrabarty and others. So, which was based on canonical perturbations theory. So, this is intrinsically, I mean, by default, it's very different because I am trying to develop a similar kind of equations from the system-reservoir theory. Now, why is it so? Okay, let me explain. Now, you can see that since this is Leonard oscillators and the two typical examples of the Leonard oscillators, now what is the general form of the Leonard oscillators? General form of the Leonard oscillators is given by this second order differential equations, where fx and gx satisfy some conditions. And what are the conditions? According to the Leonard theorem, that gx is an odd function, fx is an even function, and fx has this property, it must have one positive 0 at some x equal to xs. This is negative within some region and positive, so that this nonlinear damping term, okay, it has nonlinear damping which contains both negative and the positive damping, so that the small oscillation gets pumped up and the large amplitudes gets die down, so that the systems oscillates at some intermediate amplitude and giving rise to this limit cycle oscillations. Okay, and it says according to the Leonard theorem, then the system must have at least one stable limit cycles. Now, depending on the form, it may be even true that depending on the form of this f of x, okay, if it's a polynomial of higher degree to n, then this according to this Leonard theorem, okay, this can be even generalized to what is known as the Leonard-Smith-Levinson oscillator forms, which may include even multiple limit cycles. So, we will also do the same with the van der Pol and the Rayleigh oscillators as a general family of the van der Pol and the Rayleigh oscillators from the same interaction Hamiltonian. We'll show that. But at the same time, we have to keep in mind, since our objective is to derive these dissipative dynamics of the Leonard oscillators from the system-reservoir model, so we expect a slight modification of this present form of these Leonard equations, because as I mentioned, from the system reservoir, the damping is always accompanied by noise. So I expect a modifications of this Leonard equations, that the right hand side there must be some noise term originating from the coupling between the system and the reservoirs. Okay, and I expect a connections between this nonlinear coupling, damping, and this noise in the form of the fluctuation-dissipation relations, such that although we get the same features of the limit cycle oscillations, okay, but it may be fuzzy. The limit cycle, although it is stable on an average statistical sense, it may get fuzzy because of this presence of this noise, which is unavoidable due to its quantum origin. Okay, so this is the basic motivations or the objective, and the rest is just the analysis I am going to explain slowly. Okay, is this point clear? If there is any questions?
Yes, sir. Yes.
Yes.
Yes, sir. There is a question, it seems. Sir,
yes.
You want to raise a question, sir?
Yeah, it's okay.
No. There is a question from Professor Lakshmanan. Yeah.
Okay.
Yeah. I have a remark here.
Yes.
There exist Leonard oscillators which may not exhibit limit cycle. So a few years ago, in our department, we have studied what is known as modified Mdan equation. Okay. So where f of x is linear, proportional to x double dot plus some k x dot, plus g of x of the form omega naught square x plus k square by 9x cube. So just harmonic oscillator form. Okay. So that oscillator is exactly integrable, and it's a Hamiltonian description, and you can map it on to a position-dependent mass Hamiltonian system. Okay. And that system you can also quantize by going to the momentum space. Okay. So there exists, even in this Leonard class, certain forms of F and G for which you can have continuous periodic oscillations, and you can quantize them, and you can map on. I mean, you can have Hamiltonian structure, and you can quantize them. So even for damped, linear damped harmonic oscillator, we have shown about 10, 12 years ago, you have a Hamiltonian description. And so it's not the standard Hamiltonian form. It's more complicated, but it admits an integral, and you can identify Hamiltonian and satisfies Hamilton's equations, and you can quantize that. But it is you can quantize that in a rigged Hilbert space.
Okay.
And so you have alternate descriptions for even for damped harmonic oscillator, as well as this class of Leonard type oscillators. So one can try to proceed from that point of view to study even the kind of oscillators you are mentioning. But but I want to just point out here that there are systems. I mean, these Leonard type oscillators may have some complicated transformations by which you can map it down to Hamiltonian description. That's
okay.
Okay.
Okay. Thank you. Yeah.
Okay.
So yes. So here I would mention that yes. I mean, although I said it's a Leonard oscillators, but mostly in my talk I will mostly consider only the van der Pol and the Rayleigh oscillator and its generalizations, not in general form of the Leonard oscillators. Yes.
Yes.
Okay. Thank you. Yeah. Okay. So so can I proceed then?
Yes, sir. Yes.
Oh, okay. Thank you. Okay. So now this is the model Hamiltonian. So this is a system reservoir Hamiltonian. The first part is the free system Hamiltonian, which, as I mentioned, this is modeled as a free harmonic oscillators. The second part is the infinite degrees of freedom, okay, which again model as a harmonic oscillators. And the third is the interaction Hamiltonian. So, and this is nonlinear, as you can understand. Here, n is taken as a parameter, okay, and I will show you that n can take values 1, 2, 3, and so on. And what we have find out that van der Pol and the Rayleigh oscillators obtained in the special limits when n is equal to 1. Okay, as we will discuss. And since these are all bosonic oscillators, they obey the standard commutation relations. The systems A dagger is equal to 1, similarly B dagger and AB commutes. Now from this Hamiltonian, one can use the Heisenberg equation of motions, the standard Heisenberg equation of motions for both the system and the path operators. So you can obtain this. The first part again is the free system evolutions, and the second part is from the interactions, similarly for the path. Now what people do in this Heisenberg-Langevin approach, where you end up eventually an operator Langevin equations, you basically solve this path operator equations, and these solutions you plug that in the first equations and eventually write down a reduced equation of motions for the system operators. And if you do that, then it turns out to be an operator Langevin equations for the system operators in terms of the capital A, where capital A is a, this, you just absorb these free evolutions of the systems is slowly varying operators. And now you can see this is a much more complicated equations. This noise term that appears here is in multiplicative in nature. And here also you have a complicated form of the system operators. Now for the time being, let us focus on this just mentioned. This is the damping term which has this form, and this is the noise terms. And I expect, since I derived it from the microscopic picture, there is always a balance in the form of the fluctuation-dissipation relations. And this noise term, as it clear that it involves an path operator at the initial time, okay, bk is 0, and since this is not an Hermitian operator, you can even construct a Hermitian noise operators of this form. Now from this, it is very clear that this noise operator appears as a natural consequence of the system-reservoir coupling, and therefore the microscopic basis of such systems must be internally noisy. Okay. Now, just to show that there is a balance between this noise and these dissipations, even in this operator picture, we have to calculate the quantum statistical average of these noise operators, and this must be there as I discussed from the system-reservoir model, the fluctuation-dissipation relations between this noise and the Bath operators. So how to calculate the quantum statistical average of any Bath operators? This is the standard definitions, where HR is the Bath Hamiltonian at t equal to 0. If you use these definitions, then one can calculate the noise properties, and this noise properties first moment is 0 because it involves this noise operator f and f dagger involves only a bk and bk dagger. So there, if you take the average with respect to the Fock state, the number state basis, then it is identically 0. On the other hand, their correlation, symmetric ordered correlations, if you calculate, then it turns out to be this. Now, for the time being, now I just emphasize this cot hyperbolic factor. This cot hyperbolic factor, you can see this cot hyperbolic factor appears because this is a bosonic systems. Because this cot hyperbolic factor can be traced out to the origin of this 2n b bar plus 1, where the n b bar is the Bose distributions. And this is important to understand that this factor, these noise correlations survives or is non-zero even when t equal to 0. At t equal to 0, this Bose factor, this NB factor becomes 0. Even then, this plus 1 factor you can think of, this is due to the spontaneous emissions or the vacuum fluctuations. This, because of this plus 1 factor, you still have a noise correlations. It's a non-zero noise correlations. Okay. Now, this is clear that there is this fluctuation dissipation theorem as required for the consistency of the theory. On the other hand, the Langevin equations that I derived for the system variables, which is fairly complicated, as you can understand, because of its nonlinear nature, because it involves the system operators, both A and A dagger. Okay. Now, in quantum mechanics, the problem is these operators are no longer commuting. Okay, so they don't commute with each other. Therefore, this problem remains always in quantum mechanics, which is known as the standard operator ordering problem. And how to get rid of it? The standard method is to take an average. Okay, and this average, if we can take, okay, with respect to these with these system operators, okay, then we can get an average dynamics, and thereby we can get rid of this operator nature, because this operator Langevin equation as it stands, it's very difficult to implement for numerical simulations because of its pure operator character. So you want to get an equations which looks exactly like a classical Langevin equations. In order to obtain that, one needs to take an average with respect to some state. Now, what state I need to take the average? You can understand, because in this case, this number of A and A dagger that appears are not same. So therefore, if you take the average with respect to these Fock states, then you will end up with 0. So you have to take that average with respect to some state which is an eigenstate of this annihilation operator, and such states are well known in quantum optics community, and which is known as the nothing but the coherent state or the global coherent states. So if you take that average with respect to such coherent states, with the initial product separable coherent states of the system and the path, okay, where alpha stands for the system states and this mu stands for these different path modes. If you take this average, average with respect to these initial product separable states, you end up with what is known as the, so what you get, you end up with the C number, what is called the C number Langevin equation. The reason is that the average with respect to the system operators A will correspond to alpha. Similarly, A dagger will give you alpha star, and similarly these noise operators will become also a number where this Bk or Bk dagger will replace by this mu k0, which is the initial value of these path operators. Okay, so thereby I can obtain from this complicated operator Langevin equation a simplified, much more simplified C number Langevin equations, where this I replace, I call it C number because this now it is replaced by classical number, where this alpha and alpha star in general can take complex values. Okay, so now in order to calculate this, I take the average with respect to these coherent states and I taken a normal order prescriptions. But one can take the average with following some other ordering prescriptions. There are anti-normal ordering or symmetric ordering and so on. So depending on what ordering you are taking the average, you obtained a different kind of or different form of C number Langevin equations, and it turns out that it represents, although it apparently looks different in form, but they represent the same dynamical systems. And similarly, the C number noise looks of this form. Okay, again we have to ask these questions. What about, okay, as we have discussed, if there is this fluctuation dissipation relation is respected or maintained in the operator picture, what about in the C number Langevin equation? What is the advantage of the C number Langevin equations with respect to these operator Langevin equation? Is very clear that this C number Langevin equation, there is no operator ordering anymore. So you can treat that these Langevin equations exactly like our classical Langevin equations with this noise, which is, it is which a Gaussian white noise with the first moment 0, second moment non-zero. So you can implement all the non-equilibrium statistical mechanical techniques and calculate starting using this set of C number Langevin equations. And I am going to show from this is the kind of starting equations, and after proper substitutions one can obtain the desired form of the Van der Pol and Leonard, the Rayleigh oscillators from this C number Langevin equations. Okay, but before that, just for consistency, let me show you that this C number Langevin equations also respect the fluctuation dissipation relations as required for the consistency check. Okay, to calculate that, one can calculate how to calculate the statistical average of the C number noise. Okay, so any operator, in this case, the first average is the standard quantum mechanical average with respect to the coherent state, and the second one is the statistical average. And the statistical average is taken with respect to a initial canonical thermal distributions of Gaussian form, or the Wigner canonical thermal distribution, phase space distributions, such that it gives the correct correspondence with the operator, the proper symmetric ordered operator correlation functions of the noise operators. So you can see that once you do that, the C number noise also satisfy the same fluctuation dissipation relations. First moment is 0, second moment is non-zero. You get back the same cot hyperbolic factor, but in terms of this xi, you don't need to worry about the ordering of this operator. So that is the advantage of using this C number approach over this operator Langevin approach. But you get back the same fluctuation dissipation relations, and these noise correlations is related to this damping term. Okay, through this weight factor of cot hyperbolic factor, and this is a kind of fluctuation dissipation relations derived for nonlinear coupling between the system and the reservoirs. Normally, this coupling is taken to be linear between the system and the reservoir. This is one of the examples where we derive the fluctuation-dissipation relations for the nonlinear coupling between the system and the reservoirs. So with this, now let's go back to the general strategy, how to obtain the van der Pol and the Rayleigh oscillators, what we desire to derive from these standard Langevin equations, C-number Langevin equations. So, okay. So, whatever we have discussed so far is the following. So, we started with this Hamiltonian, the general system reservoir Hamiltonian. From there, we have shown that it is possible to derive an operator Langevin equation of this form, and it's a C-number Langevin equation of this form. This is a general form. And as I mentioned, this is a general form of the, which is valid for any n. And for our case of interest, particularly to derive the standard form of the van der Pol and the Rayleigh, one can take n to be 1. So, if we take n to be 1, the same operator Langevin equations, just if you put n equal to 1, simplifies of this form. Operator Langevin equation becomes this, and the C-number Langevin equation becomes this. Now, as I mentioned, this is derived, this C-number Langevin equation is derived from this operator Langevin equations, assuming the normal ordering prescriptions. Okay, so normal ordering means this A dagger appears on this left of these annihilation operators. But you can use these commutation relations between the operators and take that advantage, and you can write down the same operators, A dagger A square, in a slightly different form. If you use that, same operator Langevin equations can be rewritten in this form. Okay, so again, as I mentioned, these two different form of the operator Langevin equation in principle describe the same systems, but although they looks different, where M1 and M0 are any integer values you can take, it will satisfy. So you just use the commutation relations and you can derive this. Now, why I have derived that? The reason is, as I mentioned, normally in quantum mechanics, this operator ordering is a disadvantageous thing, and one derive from this to get rid of this operator ordering problem, take the average and go back to this C-number Langevin equations. But here we make use of this operator ordering problem, take to our advantage and derive our desired form, whatever form, because I derived in this way because this operator Langevin equations, although they describes, as you can understand, the same dynamical systems but in a slightly different form, but this form will help us to derive the van der Pol and the Rayleigh oscillators in their usual form, not by these equations. This C number is, it's not the ideal things to use it, but if you use this as a starting operator Langevin equation, then take the average, then if you write down the C number Langevin equations, then under the mean field approximations, you can derive this as a C number Langevin equations. Now here we made an approximations. The approximation is that a kind of mean field approximations where we neglect the quantum correlations. That means when you take this average from this operator Langevin to this, we assume that this average of A dagger A minus A, if we write down in this way, we can write down approximately this average of A product of this. Now that means we are neglecting the correlations between the operators. So under this mean field approximations, this equation is derived, and we are going to show that although these Rayleigh and the van der Pol oscillators, as it is in the classical systems, they represents very different kind of limit cycle oscillations and applies to very different context, like van der Pol may be used to explain like this circadian oscillations, Rayleigh may be used for this nonlinear mixing and so on. But from the microscopic picture, these two oscillators are equivalent at the mean field level. Okay, so this is the whole idea. Okay, so this will be our starting equations to derive our desired form of the Van der Pol and the Rayleigh oscillator. So we take this as our starting equations in the next slide. Okay, so what we have discussed so far is the following. Okay, so this is our starting equations, and also its complex conjugate is this one. And now, in order to, but although I mean this is in terms of this complex amplitude alpha, in order to identify in this the standard form of this Van der Pol and the Rayleigh, we make these substitutions of alpha and alpha star. Then we obtained a oscillators, okay, of these equations, which is, we call it a quantum noisy oscillators of this form. So we have have more, it looks very similar to this Van der Pol and Rayleigh. Apart from this M0 and M1, we have to choose so that it matches with the standard form. But also there is the presence of this noise is important, because since we derived this from the microscopic picture, so system reservoir model, so this noise is inevitable, it is always there. And this noise is, again, it is F1 and F2 represents this bath operators, which is Gaussian white noise multiplied, it's multiplicative in nature, the system operators, but doesn't matter, if you take the average, you get 0. Okay, so with this set of equations, you can obtain the various form of this limit cycle oscillations. You can choose this M1 and M0 such that it shows limit cycle oscillations, even if it may not be. You can, for a typical examples here, for examples we have plotted, this is like a classical where we have chosen M1 and M0 some values such that it shows these classical oscillations. On the other hand, in presence of this noise, if you have this set of equations, then you see you still get the limit cycle oscillations, but this limit cycle gets fuzzy because of this presence of this noise. But as I mentioned, the presence of this noise is derived from the system reservoir Hamiltonian. That means its origin is internal. This is internal noise. That means, what do I mean by internal? Means there is a relations between these dissipations and this noise. But if it is something of external noise, that means there is no correlations between these dissipations and this noise, then this limit cycle is completely lost, and we have this kind of image. So then it is destroy this stability of this limit cycle. Otherwise, as long as this fluctuation dissipation is retained, you still get a limit cycle, although it's fuzzy. Now the reason is very clear, that classically, okay, let me discuss first this now the presence of this M1 and M0. Let me explain that. What is the significance of this M1 and M0? This what we find out, that this M0, this presence of this M0 is crucial to this highest power can give rise these limit cycle oscillations, but the presence of this M0 is crucial to maintain the shape of these oscillators. For examples, in case of, if you want to derive from these equations, this Van der Pol oscillators, then you have to choose, okay, you start with these equations where F2 is your noise operators, you choose M1 is equal to 1 and M0 is equal to -1, then you get back these equations. Now these equations looks more similar to the Van der Pol one for this choice of M1 and M0, and if you make now the substitutions, proper substitutions, then you recover a proper analog, quantum analog of the Van der Pol oscillators with, although a noise term on the right hand side. Okay, now you can again derive, plot this solve it numerically. You can, this is the classical standard Van der Pol oscillators. Because of the presence of this noise, this limit cycle gets fuzzy. But as I said, that on an average, because classically you get this limit cycle because of the presence of this nonlinear term, because the limit cycle in the classical sense is purely dynamical in nature. Okay, where you have a negative and the positive damping, and they compensate each other, so there is an energy gain and loss, and so that the systems systems moves along this closed trajectory. On the other hand, here we get these oscillations purely because of the statistical origin, because here there is a balance between this noise and the dissipation terms on an average sense. So on an average, the energy is loses by the systems to the reservoir is again gained by from the reservoir to the system. So on an average sense, there is a detailed balance, and because of this detailed balance, you get this limit cycle oscillations. On the other hand, if it is of some external noise, so once you break this detailed balance, then this limit cycle oscillation is completely lost. Okay. Now this is the van der Pol oscillators. What about the Rayleigh oscillators? Now you can see for van der Pol oscillators, this is of this form of f of x is of this form. Okay, so it is x square minus 1. On the other hand, for Rayleigh, you will see that there is x dot, okay, x dot square and so on. Okay, so in order to get that, you can obtain the same set of the Rayleigh oscillators starting from the same C number Langevin equations, but you have to make a different substitutions. So for the alpha and alpha star, and this is the reason is that to get back the desired form of the Rayleigh oscillator such that one can understand this is to match with the dimensional matching, right? For examples, here for van der Pol, I substitute alpha and alpha star by x minus x dot by omega 0, which matches with the dimension of this one. On the other hand, to recover the Rayleigh oscillators, the choice of M1 and M0 is the following, which matches with this one. Now again, if you substitute an alpha and alpha star by this one, okay, so here again, in order to get this x dot, I have to make this kind of substitutions, which is dimensionally correct, and I will then recover exactly the quantum analog of the Rayleigh oscillators. Again, one can cross check with the numerics, get the similar effects. Like this is the standard Rayleigh oscillators. This in presence of this noise, and one can show that even let's say the temperature is 0, even then this still you get this noise, limit cycle gets fuzzy, and this is purely due to these vacuum excitations. On the other hand, for in presence of external noise, there is no correlations, limit cycle get lost. Okay, so what is the general strategy then? Okay, so we recovered both these van der Pol, the standard form of this van der Pol and these Rayleigh oscillators, which I have, as I mentioned, we have chosen this only form of these Leonard oscillators is that because here this g of x is an odd function which is harmonic oscillators. On the other hand, only this f of x is different. Okay, so this I chosen so that I can start with my harmonic oscillators Hamiltonian, and my choice of this nonlinear coupling between the system and the reservoir gives my desired form of the damping term with proper substitutions. Now, can I do the same thing with a generalized, with a family of the van der Pol oscillators, which may also admit multiple limit cycle oscillations? Okay, so to understand that, we have this form, okay, these Leonard oscillators. As I mentioned, that if let's say f of x is of this form a1 x square plus a0, then as I mentioned, which corresponds to this van der Pol and the Rayleigh, particularly van der Pol one, Rayleigh has a different substitution. So this is the standard van der Pol oscillators. You can obtain that, this is what we have discussed. We can obtain this starting from this interaction Hamiltonian. Because from this interaction Hamiltonian, we eventually end up with these equations, okay, where we choose my M1 and M0 such that it corresponds to my standard form of the van der Pol oscillators. How to do that? Well, for that, I just make this gamma 2 by M1 as epsilon, and then M1 and M0, I just
Sandeep, can you mute your Sandeep? Sorry
Yes.
for the interruption, sir. It's just
No, it's okay. It's okay. Yeah. So, is there any questions or in between? Or no? Then. Okay. If not, can I proceed?
Yes, please.
Okay. So then this is epsilon, and then you choose M1 and M0 such that it matches with the standard form of the van der Pol oscillators. So let me discuss first the van der Pol family, then I will discuss the Rayleigh one. Okay, so this is because the van der Pol is much more, easy to understand, because if you have this, then we make this choice and it will match with the van der Pol one. Now this is just for which admits only single limit cycles. Now you can do the same thing with the higher powers, x to the power 4, then x square x0. So in that case, to recover this form, what we have find out, you have to go to the higher order. That means, which must involve a cube, n equal to 2 then. If you do that, if you follow the same prescriptions, we obtain this. Here I must mention this C number formalisms is actually developed by my PhD group, by Professor Dev Shankar Rai. I mean, in fact, during my PhD, it has been this C number formalisms we have used in several contexts. Even during my PhD, I have used it. But we have only, up to that time, we have only used to quantum optics problem or reaction dynamics problem, but we never used to nonlinear dynamical systems. And these C number formalisms, what we have find out, it's very equivalent to the other formalisms that particularly used in condensed matter physics using path integral or the other techniques or the density operator methods. Here, following this C number approach, we follow the standard Heisenberg-Langevin approach. We recover the same results. We recover exactly the same results that is obtained from the other methods. The advantage we figure out that this C number Langevin approach is much easy to implement as a numerical techniques, because once you take this average with respect to these coherent states, it looks exactly like your classical Langevin equations. So then the way you implement your or simulate your classical Langevin equations, you can do exactly the same procedure to solve your C number Langevin equations. And it gives much more satisfactory results, but we never used it to nonlinear dynamical problems with nonlinear coupling. So this is the first time we used it, and we also find that this C number Langevin approach, even in this case, gives very satisfactory results, particularly under mean field approximations. And what we have find out that as I present that you have seen both these van der Pol and the Rayleigh oscillators is obtained from the same C number Langevin equation, or if you like, the same interaction Hamiltonian under mean field descriptions. So that means, although the van der Pol and the Rayleigh, although they looks different, classical at the classical level, but it's quantum analog. Definitely the noisy quantum oscillators, noisy van der Pol, noisy Leonard, is equivalent at the mean field level. So you can derive from the same microscopic interaction Hamiltonian under C number Langevin description. So this is one of the findings in this work. Okay. Now coming back to this, whatever we are discussing, that one can derive even the higher powers polynomials of f of x from this form of this interaction Hamiltonian, where the C number Langevin equation is given by this. Similarly, the same substitution as we have done, okay, you don't need to change the substitutions. You can exactly get back this form of this dynamical equations with whatever. So now once you get these equations, you can identify what is your epsilon. So in this case, epsilon would be this. Then A2, A1, A0, you can identify with these values of these MJs. And we also formulated a general prescription of the relations between these AI and these MJs. I am going to show you. And second thing, we have shown that this methods is not only applicable only for single limit cycle descriptions, but even can be generalized to multiple limit cycles. Let's say, for examples, here it is polynomial of degree 6, then highest degree of polynomials, and this Leonard meets Levinson form says that if it is of this form, if it is a f of x is highest degree of 2n, then and these AI are alternating in sign, then this system at most can admit n number of such limit cycles. So in this case, you have three limit cycles, 2 are stables, and you can again see that in presence of this noise makes this limit cycle fuzzy. So we have also checked that this works even for multiple limit cycles. And with this, let me generalize this techniques to any arbitrary polynomial of f of x of degree 2n. Okay, so to do that, so this is the kind of, we said this is a Leonard-Smith-Levinson form of the van der Pol and the Rayleigh family. So just first let's discuss the van der Pol family, where the f of x is of this form, f a highest degree of x to the power 2n. To obtain that, you can understand from the method that I have discussed, from n equal to 1, n equal to 2, just by mathematical inductions, you can understand this would be your desired form of the interaction Hamiltonian. If you use this as your starting interaction Hamiltonian, from there you can derive your generalized C number Langevin equations, which matches with, recover this form of this, and after this proper substitutions for the standard van der Pol oscillators, you can derive your generalized versions of this quantum van der Pol oscillators, although it's noisy, and you can now, relate what is the general expression for this AI which appears in your polynomials and these MJ, so that you can derive, okay, so you can construct, so you can judiciously choose your MJ such that it exactly matches your desired form of the general form of the van der Pol oscillators, which admits n at most n number of such limit cycles. So this is for the van der Pol oscillators. What about for the Rayleigh one? Exactly the same thing, only as I said, the difference is that there is no difference between this van der Pol and the Rayleigh as long as this description is considered. The only difference is the substitution. So they can be derived from the same C number Langevin equations just by changing the substitution. So if you change the substitution from this to that, so you can even obtain a general versions of these quantum Rayleigh noisy oscillators, where this again you can identify the relations between these coefficients beta and your AI, which is this is your beta j. Okay, so this is for van der Pol. So in this case, it is beta with these MJs, and this is given by this expressions.
Excuse me, sir. There is a question from a
student. Yes.
Please see, you can raise your question now.
How do you choose those alpha for van der Pol and Rayleigh?
Sorry?
How do you choose this alpha is equal to half x minus I x dot? That one for van der Pol and half 1 by 2 omega x minus I x dot for Rayleigh. How do you choose?
Okay. So this initially, see, I mean, these for harmonic oscillators, this alpha is essentially these coherent states, and this has a dimensions. So from that you can have a guess, but so this is kind of, this is a standard substitutions. This substitution just by, if you just make some trial and error, the p factor, okay, you can figure out. But it is dimensionally, it is, you can understand this is. Sorry? Yeah.
Yes, sir. So sorry, some interruption. Please go ahead.
Yeah. So this you can just identify with these dimensions, that it must be dimensions of this position. So then if you have x dot and then you have to divide by these omega 0 and so on. So, I mean, well, these substitutions, there is no way, I mean, there is bit of trial and error definitely is there, but these substitutions you can understand if you look at, for examples, if you have given these equations, you can understand to get back from this equation to this one, you have to have these substitutions. Okay, so this you have to do something trial and error. So if you have this alpha dot, then if you have x dot only, then you get this x double dot and so on. So this is just by dimensional analysis this has been done. And this is the best choice. Yes.
Dr. Ghosh, you are just making a transformation from C number Langevin equation through these substitutions.
Yes.
So why do you then call the resultant equation as quantum equations, quantum oscillators?
Sorry?
Why do you call them as the resultant equation in terms of x as quantum van der Pol or quantum Rayleigh and so on? Still, it's a C number equation. After this substitution, alpha equal to half omega naught x minus a x dot.
No,
so
as I said, okay.
Yeah.
Okay, so as I said, these C number Langevin equations, although it looks like a classical Langevin equations, but if you look at the fluctuation dissipation, then it may satisfy, it's not gamma kt. Okay, noise-noise correlation is not like classical fluctuation dissipation, it is cot hyperbolic, and cot hyperbolic includes both. I mean, it's valid, it's 2n bar plus 1. So because it's even presence, even if you have temperature 0, so even then this quantum fluctuation is still there. So that means this C number Langevin equations is purely, although it looks like a classical equations, but it is quantum mechanical in content. So that's why we called it as a quantum Langevin equations.
Okay.
Because it is these fluctuations even presents at t equal to 0, which is purely due to vacuum fluctuations. It cannot be, I mean, classically you don't have fluctuations at t equal to 0, but so this is still there due to quantum origin. So that's why we call it.
Okay, thanks.
Yeah. So okay, so I am almost done. So okay. So yeah. So as you can understand, okay. So then you obtain this generalized version of the Rayleigh oscillator. So with this, I conclude. So what we have discussed is that based on a system-reservoir model and appropriate choice of nonlinear coupling, we have explored the microscopic quantum generalizations of these oscillators. As Professor Laxmanan mentioned that yes, there might be some non-trivial Leonard systems, so I should be more careful calling it as a general, I mean, should call it as a Leonard system, but well, okay, to rectify it, it is kind of van der Pol or the Rayleigh family of Leonard systems or their generalizations. And in these formalisms, we make an extensive use of harmonic oscillator coherent states and the canonical thermal distributions of the C number noise for these path variables, and based on that we derive these quantum Langevin equations of the reduced systems, which may admit both the single and the multiple limit cycles. And we have shown also that the detailed balance in the form of the fluctuation dissipation relations, this is very important in order to preserve the stability, dynamical stability of the limit cycle oscillations. And even in case of t equal to 0, so this can be even preserved, the limit cycle oscillations still gets fuzzy even at t equal to 0 purely due to vacuum fluctuation, which is purely quantum in origin. So in that limit, definitely it's a quantum oscillators, or and the quantum versions of this Rayleigh, van der Pol and several other variants of them can be derived as a special case of the theoretical scheme as I presented, but within a mean field descriptions. This is very crucial, that we have shown that under the mean field, If you neglect these correlations, only then you could recover, you can show that these noisy, at least these noisy oscillators, this van der Waal and the Rayleigh, they are equivalent. Otherwise not. At the classical level, as it stands, without this noise, they are very different origin. On the other hand, and a large number of Leonard systems differing in their form of being. So, and also we have only discussed the van der Waal and the Rayleigh can be derived from the same interaction Hamiltonian, but it is evident that that this limit cycle is mostly guided by the highest degree of the polynomials, but all the other lower powers are required to obtain the actual or the desired form of this limit cycle oscillation. So they actually maintain the shape of this limit cycle oscillation. So based on that, you can in fact from the same interaction Hamiltonian, so this is another findings, that although the various nonlinear oscillators may differ in forms, but they can even be derived from the same microscopic Hamiltonian, same microscopic interaction Hamiltonian. As an example, so we have discussed only the van der Waal and the Rayleigh, which is most simplest because they can be modeled starting with the harmonic oscillators. They are free term, and only you just model this nonlinear damping through the interaction Hamiltonian. And this can be again derived from the same microscopic Hamiltonian at the mean field level. So with this, I conclude and thank you very much for your kind attentions.
Thank you, sir. Thank you.
Thank you. Thank you so much.
Now, the forum is open for clarifications, discussion.
Yes, sure.
Questions. Questions from students? Yes. This go ahead.
Sir, this C number quantumizing, is
Yes.
that it is distributed according to the Leonard distribution function. So,
Yes.
is it because of the presence of cot-h function, or we can choose another distribution function as well?
Yes. You can choose. You can even choose only these with you choose even this only the Bose distribution function. So it depends again. The Wigner distribution functions is chosen because it's a phase space distribution functions, because we calculate to show the correspondence between this operator Langevin and the C number Langevin picture. Because this operator Langevin picture, as we have seen, that this noise operator, we take a symmetrized order. So once you have the symmetrized order, you have this A dagger plus A dagger A. So if you take this average quantum statistically, you get 2n b bar plus 1. So that gives you the cot hyperbolic. So that is your answers for this initial distribution. If you have normal order, you can have different distributions. You have to choose these answers as a distribution such that there is this correspondence must be maintained between the C number Langevin and the operator Langevin. Only then your formalism, the theory that you are developing is consistent.
Okay, thank you.
Yeah.
Right. Yeah. Dr. Banerjee, you can go ahead.
Yeah, good afternoon, Dr. Ghosh. Very nice lecture you have delivered. I have one query actually. In open quantum system, we deal with, generally we deal with quantum master equation.
Yes.
What is the advantage of your type of formalism?
Yeah, I mean, okay. So these open quantum systems normally derived. I mean, there are various methods like these density operator methods that you mentioned. This master equation approach, that is another very powerful methods. Yes. So these two methods are equivalent. I mean, as such. But we use this over. I mean, they particularly follow this method here, particularly because if you derive this density operator method or the standard master equation approach, you don't get this Langevin equation. So the Langevin equations always have the advantage. You can have this classical deterministic equation of motions. Then you introduce these fluctuations. And this noise term is there. So you can, I mean, physically it is much more insightful. On the other hand, the density operator, you can then, from the master equations, you can derive the Fokker-Planck equations. You look up this, then the probability distributions in this phase space. So you construct either P distribution, W distribution, and so on. So based on that, so I mean, both these Heisenberg-Langevin approach and this master equation approach are identical and equivalent. People use it depending on the context, because here we use it because it looks very similar, because I cannot do the same thing. I can definitely derive, okay, what about these limit cycle oscillations looks in the Wigner phase space distributions. But since I want to visualize exactly the limit cycle oscillations, I prefer Langevin over this density operator. So that's why I use this Heisenberg-Langevin. Okay, and the C number Langevin in our previous group, it was proposed particularly in this context, that if you derive the standard Langevin equations, which is an operator in nature, because of this operator ordering problem is very difficult to implement for numerical simulations. But if you take the average with respect to these coherent states, then the Langevin equation, the C number, it now looks exactly like your classical Langevin equation. So now you can implement. So that's how it becomes more useful or advantageous.
Okay.
Yes.
That is clear to me. And one more thing I find very interesting in your slide with the biorhythmic oscillation.
Yes.
In the biorhythmic oscillation, what I have seen that your quantum noise does affect the stable limit cycles.
Yes.
But it appears from your picture that it does not affect the unstable limit cycle.
Yes. No. Yeah, that is true. I mean, this is also we have find out. But what would happen to the unstable limit cycle is not even clear to me. I mean, this is what we obtained from, I mean, this cannot be, I mean, I don't know. I mean, for analytically how to identify or to justify to look at it, this is what, when we simulate this, so the idea was, okay, we tested with the single limit cycles, then we go on, whether it is only restricted to single limit cycles or it is also gives such noisy limit cycle gets noisy in presence of this internal noise also for multiple limit cycle, and this is what we obtain as a numerical solutions. But yes, I also agree. I mean, this maybe we can think of. I mean, I am not sure. Yeah, this answer is not very evident to me.
Okay, thank you again. Nice talk.
Okay, thank you so much.
Questions from others? Any other student? Prashant, you want to raise some questions?
Hello, sir. Hi, sir.
Prashant?
Yes.
Hello.
Prashant, what is your question?
I think there is internet problem.
Dr. Ghosh, it is a very beautiful lecture,
Yes.
so I really enjoyed it.
Okay, thank you.
Can you again explain to me what is the significance of this? I mean, how do you interpret this M0 and M1, M2? How do you identify these parameters?
Okay. Okay, so for example, let me. Okay, so in this case, for examples, I first derive this, then I need to derive from, this is the C number Langevin. I need this to identify this as explicitly as a Van der Waals oscillators.
Yeah,
Now,
but where do you get this M1 and M0 in the C number Langevin equation? How do these parameters arise?
okay. So this appears even before. Okay, so let me. Yes, here. So here, if you this appears because of this one, because as I said, if you have the standard operator, this is how you get for n equal to 1, a dagger a square.
Yes.
Now, so if you take the average with this normal ordering, you get this standard form. Now, what you can do, you just forget this C number Langevin, you start with this operator Langevin, use the commutators. Use this, write down this a dagger a square in this form. Okay, so this is another form. It's I mean, even if let's say if you use that, then you can so now you have a different combinations of this a dagger a square. So now you have a dagger a square, also you have a dagger a of these combinations. So if you just add something here and subtract something there, okay, so if you do that, so here what I do, like M1 cancel, so I exactly write the same thing. So I exactly write the same equations with this one, because a dagger a square and this one is same, right? So I here I subtract m0 by m1, here I add m0 by m. Okay. Now I take the average with respect to again the coherent states and neglect the quantum correlations.
No, my question is, how do you get the arbitrary parameters M0 and M1?
No, I mean, what I am saying, I can always write, let's say I don't know, this is kind of undetermined numbers. I will decide later on. Based on how do I want to identify the form of the polynomials, like say for Van der Pol, Rayleigh. So based on that, I will choose my M1 and M0. These are kind of free parameters. But from this, I can always write this.
Okay, thank you.
Because M1 and M1 cancels. So essentially, because a dagger a square is same as this one. So here I add M0 by M1 of this, and here I subtract. So here I subtract, here I add. Now I average. Take the average. Once I do that and use this mean field, I will get this. So what I claim that from these same equations I derive two C number Langevin equations which looks different in form, this one and this one, but they describe the same dynamical systems under mean field.
Okay.
This is the point. Now I choose my M1 and M0. Up to you. This is up to now me. Now, how do I identify M1 and M0? Depending on whether I want to identify it's a Van der Pol or the Rayleigh. That's how I choose it. So this is kind of all free parameters, and so these free parameters are restricted by these conditions. How do I want to identify this with this standard form of this Van der Pol and Rayleigh? And I discussed with this general form, and there is a general relations between them. As I mentioned, yes, this is the general relations between. If you have this one, if you want to have this polynomials ai various ai, then your mj so then there is a relations between this mj with this aj. These relations for the Van der Pol oscillators.
Thanks.
Yes.
Dr. Ghosh, are you able to read your chat box? There's a question.
Okay, let me check. I'm not sure. Where is the chat box? So can you read it for me?
Yeah, sir. Noise is not defined one, right?
Sorry, which one?
Noise is not defined one. That is the question he asked.
Mass.
Noise is not defined one. So how it is affect against dissipation to achieve stable limit cycle?
Sorry, I didn't get. Noise is not defined?
Noise is not defined one. right? That is a word he put. So can you come? Yeah. No.
Okay, so noise here has the statistical properties. It's a Gaussian noise, so that means you can generate as a random number. So this is how it is implemented in the numerical simulation. So you generate random number distributions which satisfy these conditions, statistical properties, and that will give your properties of this noise. So that you implement there. That's it on the right hand side as a noise.
That is
so
what he asked.
Yes.
In
Sorry.
what way noise can be defined? In what way noise can be defined?
Oh, okay. So maybe here, if I come, okay. So this here in this these Langevin equations, this noise essentially is a characteristics of the So what happens? You start with your system reservoir Hamiltonian. So you have your systems, you have your reservoirs. Then what you do? You eliminate these infinite degrees of freedom of the Bath variables. Okay. And write down the reduced dynamical equations for the systems only. So the Bath property only appears through the system, these equations only through the noise. So this is where the Bath degrees of our Bath properties, I would say, appears through this noise. So now you choose what kind of Bath or the statistical properties of Bath you would like to introduce through these noise correlations. Does it answer these questions?
Yeah, Prashant? Prashant, are you listening? Yes, yeah, he said okay.
Okay, thank you.
He said okay. So, any more questions from students? Yeah. So we are not getting any questions.
Okay.
So
Okay.
let us,
Yeah. That's fine.
So there is a question from Tanmay Banerjee.
Sir,
Actually, I have already asked the question and I forget to just deactivate the raise hand.
Okay, okay, since we are not getting any questions, I would like to conclude the session by thanking Dr. Arnab Ghosh for giving a very interesting talk. By accepting our invitation and giving a very interesting talk on quantum Leonard oscillators. Thank you, sir. Thank you very much. Thank you.
Yeah, thank you so much. Okay, let me